In this work, we propose a novel approach to learning probabilistic sentential decision diagrams, or PSDDs for short. So first things first, what are PSDDs? PSDDs are structurally decomposable probabilistic circuits capable of encoding logic constraints as certain knowledge and uncertainty through learned probabilities. Importantly, inference queries such as probability of evidence, marginals, conditionals, and more are all both exact and tractable in PSDDs. In a nutshell, PSDDs are recursive decompositions of logic formulae into disjunctions of conjunctions. As an example, let's take the circuit here on the right. A PSDD is an OR gate whose children are AND gates. Each AND gate has as input two formulae. The one on the left is called the prime and the one on the right the sub. We then recurse over all primes and subs up to literals. This decomposition is guided by a V-tree, here seen on the top right. The V-tree decides which variables go to the primes and which go to the subs. The parametrization of the edges coming from OR gates gives a probabilistic meaning to the circuit. The value of OR gates is simply the weighted sum of its children, and for AND gates, the product of both its prime and sub. Literals act as indicator functions. Despite all the upsides of PSDDs, there's little work in how to learn them, especially when it comes to learning a PSDD from logic constraints. As far as we know, there are only two previous works on effectively learning PSDDs. The first is Learn PSDD, which despite yielding very good results has some limitations. First, it doesn't learn the circuit from constraints, rather requiring an initial PSDD to be passed as argument. Usually, this initial structure is compiled from a CNF or DNF into a minimal logic circuit representation, meaning variables not mentioned in the constraints but modeled through probabilistic influences will be trivially represented in the circuit. Once this initial structure is built from some external program, Learn PSDD then grows the circuit by the local transformations shown here on the right. These transformations don't change the encoded formula, but increase the number of parameters, changing the underlying distribution. Unfortunately, this approach requires an evaluation of the whole circuit in order to select which candidates are grown, which is quite costly. The second existing learner is Strudel. It works in a similar fashion to Learn PSDD, but uses elaborate heuristics to speed up the evaluation used in order to select the better candidates. This allows Strudel to scale up to high dimensions, as long as the circuit isn't too big. Strudel also proposes a way of compiling an initial structure from a childhood tree, although this compilation looks exclusively at the data and ignores logic constraints. Our work tries to solve the issues from previous learners by providing a fast algorithm capable of learning a structure even under high dimension and complex formulae. Our approach, which we name Sample PSDD, is also consistent with some constraints, although it does come with drawbacks. First, tractability is achieved by sacrificing some consistency through a relaxation of the formula. And second, performance is dependent on how much we're willing to sacrifice, as well as the structure of the given V-tree. To better understand how our algorithm works, let's look at an example. Take the formula given by phi here in the slide. Our approach assumes that the primes are always conjunctions of literals. This makes extracting the subs simple. It's merely the restriction of phi by the realization of the primes. As we can see here in the example, the primes become all the possible combinations of positive and negative literals, and subs the corresponding restrictions. This presents a problem though. Obviously, the number of primes will be exponential, and therefore the circuit size is going to explode. So let's come up with a solution. Let's randomly sample a bounded number of primes and call it k. So here in the example, we have the same formula as before, but with a slightly different V-tree. If we were to enumerate each and every prime, we'd end up with 2 to the 3 primes. Instead, we're bounding our primes and sampling only 3 of them. Here we sample A and B, A and not B, and not A. The subs are then the respective restrictions, and we end up with these 3 subs over here. Now here we face yet another problem. This violates structure decomposability. Why? Because the variables here in the subs are not in this set here S on the right of the V-tree. That is, the sub not C and D contains C, which is not in S. And the sub B and not C and D contains both C and B, which are not in S. So how can we solve this? The solution that we found was to relax the logical constraints, that is, the subs which violate structure decomposability. So here on the left we have the same partial PSDD that we had on the previous slide, but we relaxed all the subs so that they no longer violate our requirements. This relaxation is pictured by this binary expansion tree, where at each node we either expand a variable into positive or negative literal. The leaves are the resulting primes, and subs are then set as the restrictions after they are applied this forget function. This function forget essentially sums out the variables which are not in S, and so we end up with the subs on the left here, which all respect S. To evaluate our method, we sample 30 PSDDs through the Sample PSDD approach, and use 5 ensemble strategies to evaluate their performance, namely likelihood weighting, where we set 30 PSDDs as components of a mixture whose weights are proportional to the likelihood of each PSDD in the train set, uniform weights, EM and stacking, where we learn only the weights of the mixtures through the respective methods, and Bayesian model combination. We compare these 5 strategies against Strudel, Learn PSDD, and Learn SPN. We use several data sets to evaluate the performance. The graphs here on the right show the test log likelihood results for the lead and lead plus images data sets in function of the trained data percentage used for learning. The lead dataset is a toy problem that models a faulty 7-segment lead display for showing digits. Each segment is assigned 2 variables, one for its observable state, that is, if it's on or off, and one for its latent state, that is, was it supposed to be on or off. We impose logic constraints on the latent variables according to configurations that represent valid digits. The lead plus images variant worked similarly, except the latent space is a 10 by 15 black and white image, and the constraints are on the pixels. The 2 next datasets are based on the well-known Kamishima sushi dataset, where 5,000 rankings are laid out for 10 sushi types. The sushi ranking variant models preference the same way as the setting proposed in Choi et al. 2015. We also use the sushi top 5 variant, as proposed in Shen et al. 2017, where only the best of 5 in each ranking is shown, ignoring the preference relation between elements. This is equivalent to a 10 choose 5 cardinality constraint. The last dataset also relates to cardinality constraints. The Dota 2 dataset contains almost 103,000 results of game matches. In the game, each team chooses 5 characters out of a pool of 113, making this 2 113 choose 5 cardinality problems. Since CNFs aren't able to encode this big of a cardinality problem, we had to initialize Learn PSDD with a structure compiled from a binary decision diagram. Learn SPN also ran into trouble when learning, quickly running out of memory at more than 50% of the data used for training. In summary, throughout all datasets, we found that our approach fares better with fewer data, yet still remains competitive even under lots of data. We also evaluated the time it takes to run each algorithm. On the bottom right, we have the time it took to learn Strudel, mixtures of strudels, and Learn PSDD, all with 100 iterations each, as well as the first 2, strudel and mixtures of strudel, with 1,000 iterations. Finally, we also have the total time it takes to sample 100 circuits with sample PSDD. We also note that our method is naturally parallelizable, which allows us to get the good run times even when sampling a large amount of circuits. Finally, we also show that the choice of a bigger K positively impacts both log likelihood and consistency with the original constraints. We also empirically show that this also happens with more right-leaning V-trees, that is, V-trees which tend to have more variables on the right. This, however, does come at a cost of circuit size and time taken to learn. Well, that was our work. You can find more information in our paper, and I hope to see you at the poster session. Thank you.